Hello there, class. This video is going to be addressing the very last objective of the unit. That would be objective 1.5, which is to determine the continuity of a function using limits. Some of this stuff is really intuitive, and so in this first screen, what I have here is the picture of f of x, and I'm going to ask some questions without defining continuous formally, and you'll see what I mean by intuitive. So what does it mean to be continuous? Well, here we go. We're going to take a look at continuity in there's three ways. We're only really going to focus on continuity at a point, on an interval, and overall, we're not really going to focus on that. We're just going to really look at point and interval, but you could describe it overall as well. Look at the first example. It says, is f of x continuous at x equals 3? So you see here that it has a nice closed point. You see that there's really no disruptions in the graph, and when that happens, we really are continuous. I could draw this point, or I could draw this point without lifting my pencil in the function. So I'm going to go ahead and say that x equals 3 is a yes, continuous. Now at 2, it's not undefined, because if you were to ask for the y value at 2, the y value at 2 would be 2. But you do have a discontinuity because, you can see here, sorry, it's kind of sloppy, but you can see here that you really couldn't draw this part of the graph without lifting your pencil. You've got a gap and then the point on top. So I'm going to go ahead and say that that's a disruption at x equals 2, so no, that is not continuous. At x equals 1, you have a huge disruption. In fact, you have a jump. So if I think about that, that's a huge disruption. That's definitely not continuous. Again, continuous would mean something that looks really good in terms of well behaved, and it does not have disruptions. Now I'm going to erase this a little bit so that we can talk about intervals. So the three questions we answered before were specifically at a point. We're now going to be asked about intervals. So what about from 2 to 4? Well, from 2 to 4, everything seems good, except there's an issue here at 2. But if you notice, the interval doesn't include the 2, so everything between 2 and 4, including the 4, looks to me continuous, no disruption. I would say yes. Now, if you look at the other one, 0 to 2, all right, 0 to 2 goes from here, 0, all the way to 2. From 0 to 2. Well, there's a huge issue here at 1. And because of that, we would have to say that, no, that is not continuous. So this is sort of the intuitive way of looking at it. Continuous meaning no disruptions, everything's nice. Let's go ahead and define it formally. In terms of calculus, we are going to define continuous at a point in this manner. A function is continuous at a point, at an interior point, C, of its domain if the limit as x approaches C of f of x is f of c. And by interior point, I just mean if you're talking about an interval, interior points is everything in between. Now, this statement that we just made is going to be super important, and I'm going to ask about it often. If the limit as x approaches c, I'm going to kind of highlight it here. The limit as x approaches c of f of x is f of c. That's three things, really. This statement means that first, the limit exists. Second, the y value exists, that's the f of c. And the third statement that is being made here is that both the limit and the y value are equal. So that's how we define continuous using calculus. Now, let's look at some examples. Let's take a look at x equals 2. At x equals 2, I would ask you intuitively, is it continuous? My hope is that you would say yes. Now let's think about it using the calculus definition. Does the limit exist at this point? You see here the left side and the right side both approach 1, so the limit does exist. Does the y value exist? Well, f of 2 is 1, so it does exist. And then the last question is the limit 1 equal to the y value 1? In this case, it's yes. So yes, the function is continuous. You could think about it intuitively, but we do have this definition to help us. How about negative 3? Well, at negative 3, let's ask ourselves the same 3 questions. Does the limit exist? Well, the limit does exist. The limit's negative 1. But does the y value exist? Well, it does. The y value is at 1. And finally, does the limit equal the y value? Well, the limit's negative 1 down here, but the y value is 1. So in that case, we were not able to answer yes to the last question. So it is not continuous. All right, now we're going to come back and look at 4 in just a moment. How about negative 1? Well, at negative 1, the limit from the right does not equal the limit from the left. So pretty much I'm done analyzing, because if the limit doesn't exist, the function will not be continuous. So no on the negative 1. On the positive 1, we have the same exact problem. So we also know that we have no. The limit doesn't exist there, so we have a no. Now what about 4? 4 is an endpoint. So if you notice, I have a definition for continuous at endpoints here. And basically what that means is that if the limit as x approaches a being your left endpoint, equals the y value, of course that limit has to come from the right because it doesn't exist on the left, then the function is considered continuous at that endpoint. The same thing for b, except it has to be coming from the right. So if we take a look at 4 right here, the limit from the left side is going to be negative 1, but then the y value is a completely different value, which is a 1. So I would have to answer no. Okay. Now I didn't put it in here, but what about x equals negative 4? At x equals negative 4, see here, you have the limit going to negative 2, and the y value is negative 2. So if I were asked about negative 4, I would say yes. Basically, endpoints are continuous as long as they do not have any gaps in them. Okay? All right, let's take a look at the next slide. Okay, the next slide is about being continuous on an interval. And in order to be continuous on an interval, you simply have to have continuity at every single point in the interval to include the endpoints if that's what the interval states. So let's take a look at negative 4 and to negative 3. If I start at negative 4 and go to negative 3, but I do not include negative 3, there's an issue here at negative 3, but the interval doesn't include it. So everything in between looks pretty good. So I would say yes. Let's try one more. This time it says from negative 4 to negative 3, but you include the negative 3. Well, there's a clear discontinuity. You have a gap in a y value up here. So that, of course, is no, because if we're going to say it's continuous, it must be so in every single point in the interval. Negative 1 to 1. I'm going to go ahead and ask you to pause the video, try the rest of them, and then compare with me when we come back. So these are my solutions. Again, the function must be continuous on every single point in the interval if the interval is going to be considered continuous. So notice, for example, negative 1 to 1, including the 1. Well, the 1 has a gap here, so that's going to make it a no. Now check out this one right next to it, negative 1 to 1, where negative 1 is included. And you might say, well, Ms. Valdez, this is has a huge jump here. Why in the world would you say that? It is continuous. Well, the reason it's continuous is because the interval asks you to look only from negative 1 to 1 not included. So that means you're not going to look anywhere outside of that. And if basically you were to erase the graph everywhere else, you would have a nice line segment from negative 1 to 1. And it would be continuous. Closed at negative 1, open at 1. Okay, so you're really not considering the left side of that negative 1, which would make it a jump. So those are my solutions.